Okay, good morning, everyone. Welcome. So today we're going to start different topic and discuss radiation and physics and things like that, which we'll spend a couple of days on. So this is going to be, well, it's different from the linear system stuff in that this is a lot of, well, terminology, concepts, relationships, some equations, but most of the equations are pretty simple. So we'll get into that in a second. Most of you actually have already responded to the doodle poll that I just sent out. So yesterday we had kind of a virtual office hour, which I thought is pretty useful as a time for people to ask questions, especially about homework assignments and things. So it would be good if there's going to be a common time that we could just reserve for that each week where, well, at least almost everyone is available, everyone who cares. So we'll see how the poll shakes out and try to set a time for that. I'm going to record those. I recorded the one we had yesterday, and it's up on the channel. So if you can't make it to one, fine. And I'll be on at that time. If nobody shows up, then I'm not going to sit around and wait. Okay. And of course, you can always schedule another time if you need to. If you'd rather have a one-on-one question and answer, or if that just doesn't work out for you, drop me an email. Okay, we'll figure it out. That's how we kind of started the one yesterday. So before we barrel into the radiation material, does anybody have any questions on material that we've just done on the linear system stuff and contrast, resolution, noise issues? Any questions? Okay, well, there'll be a chance at the end too if you think of something. But for now, we're going to go ahead and push on here. Okay, so here at the beginning of the course, we're kind of setting some foundations and kind of, well, reviewing some things that, well, are at least prerequisites, or but also extending those a little bit into the areas we're going to be talking about. And the same is true with physics. Some of this you will have seen before and probably forgotten. Some of this maybe you haven't seen before. In any case, so we're going to be talking about what radiation is, what forms it takes, the two primary kinds, which are particles and waves, essentially. And then some of the issues around, well, radiation produced by isotopes and radioactive decay. And I'm not sure if we'll get through all this today, but we'll see. Okay. Well, so radiation, right? What is it? So generally, it's just energy that travels in one of two primary forms, waves or particles. And that's kind of an interesting thing that we refer to radiation in both of those things because they're physically very different things, as we'll see, but that's what we mean. So our radiation may or may not have mass, may or may not have charge. And I guess, in the sense that, okay, it's not too hard to see traveling waves, electromagnetic waves as energy. Subatomic particles may not be, immediately obvious, but Those particles, moving particles, have mass. Actually, standing still particles have mass, and so there is mass energy associated with those, according to E equals mc squared. We'll talk about that. But also, if they are actually moving, then they have kinetic energy as well. So that is energy traveling through space. So our radiation may or may not have mass, depending on whether it's a particle or a wave, and may or may not have charge, as some of the particles can be charged and some not. So we'll see. Now, for purposes of certainly any kind of medical imaging or any kind of radiation biology, we're mainly concerned with ionizing radiation, which basically has enough energy that if it interacts with an atom, could ionize the atom by essentially kicking out an electron, right? And so you can think of it as a collision, right? Our radiation deposits some form of energy into an atom that it collides with or comes very close to, and that causes the atom to lose an electron. Once the atom loses an electron, it's an ion, and in fact an ion pair, because there's an electron floating out there too, which is an ion. And the whole point, as we'll see a lot more when we talk about radiation biology, is that radiation that ionizes is capable of causing damage. Okay, because once you've produced an ion pair, then that can react with something else. That's the basic idea. So ionizing radiation is generally considered to be in the range of, roughly greater than 13, 14 electron volts. And you'll be seeing these units a lot. If they're not familiar, they will become familiar. There is a conversion with joules and other units of energy. However, the key thing here is that when we're just to kind of set the space a little bit, when we're imaging with, say, X-ray, we're imaging at 20 keV or above, so 20,000 electron volts. So we're working in the imaging world in areas much, much higher than this. Okay, so definitely we're in the ionizing range. If you're below that, then you are non-ionizing. And it's really, doesn't have enough energy to produce to kick an electron out of a shell. If it deposits its energy, it just causes a little heating, essentially. And so, that's generally what we're talking about here. And as noted, if we produce ion pairs, they are potentially reactive with other things and could cause biological damage just by reacting into a form and basically creating reactive oxygen. You've heard of antioxidants, which are supposed to fight reactive oxygen floating around your body, which can do is supposed to be able to do all kinds of nasty things. So, okay, so there is a whole kind of range of the electromagnetic spectrum. Seen charts like this before, probably. And, we're ranging from AM radio here up into radar microwaves, infrared, into the visible light spectrum, ultraviolet. And then it's not till we get up here in the higher energy, also higher frequency and smaller wavelength area that we're really talking about the kinds of things that we're going to use for our imaging, right? There are applications, and plenty of them, of visible light imaging, which is in a sense not that different from X-ray and gamma ray, except we kind of use different models to think about them in a lot of ways. The reason is here in the visible light range, you kind of have to work, because of the scale of wavelengths, you have to be thinking about them as waves and worry about things like refraction and other interactions that on the scale of the wavelengths of our X-rays and gamma rays here, just are not as, for most of the applications that we do, just aren't as much of a problem. And so, you know, the biggest difference, as we'll see, is that we generally think of these as photons, which are a, you know, a kind of a imaginary construct to treat them as particles and have them behave as particles, even though they don't have mass. Okay, so we'll be careful with that. Whereas you can, you know, there are applications where it makes sense to do visible light and treat it as photons in little energy packets, but also a lot more applications where you have to be thinking about refraction effects and other kinds of things that are interference and things like that, that are generally, those things exist for these types of waves also, but the scales are so different that in most of our applications that doesn't matter. In some applications, you know, they do diffraction of X-rays and use it, certainly in materials science, you know, for doing analysis of materials on very small scales, right? You're getting down to much smaller scales than we're talking about for medical imaging. Okay, so the point is, this is all electromagnetic radiation, right? And the only difference really comes in, okay, well, either frequency, there's a correspondence, as we'll see, between frequency, wavelength, energy, all of those things are related to each other. And so the fact that we're working up here with things that have enough energy to penetrate through the body, whereas, you know, down here, the penetration is extremely limited, okay? For some reason, the near IR has some special properties with a little bit of additional penetration through biological tissues, but it's not, you know, not really till you're up here that you could actually get all the way through a significant amount of tissue, right? Which is what we do in a lot of these cases. So that's the main distinction. Most of the rest of these, you know, if they impinge on your body, will be converted to heat and absorbed very quickly. Okay. It certainly can't pass through. In fact, you know, ultraviolet, which is potentially damaging, is ionizing radiation, you know, can only get through the first, you know, millimeter or two of your skin, but that's where it causes damage. That's why you're supposed to wear sunscreen. So, okay. So, you know, that kind of sets a scale. As I will point out, there's not, well, the mystery difference between X-rays and gamma rays we will get to. Okay, so as I've referred to, our forms of radiation can be particulate, right? And so these are particles and have mass. So familiar things like protons, neutrons, and electrons. Less familiar things like positrons and alpha particles. Or electromagnetic radiation, which, as noted, has no mass and basically is anything on that scale we just looked at. And so, you know, there are practical examples of these in producing X-rays, as we'll see when we look at X-ray systems. Actually, producing X-rays uses both of these types. In fact, PET radionuclides, in fact, also use both particles and electromagnetic radiation. And so in these examples of imaging systems, actually, both of these types are involved. Okay. So this is just a little bit more about the idea of ionization and excitation, technically a difference. And so when radiation of either type interacts with an atom, then ionization occurs when we actually eject an electron from the atom, and therefore it's got an open space out in the orbitals, right? And is ionized and could, well, let's say it's more likely to bind with something. An excitation case is basically not enough, the energy deposited in the atom isn't enough to actually eject the electron and ionize. It just pushes it to a higher energy state, an orbital. So that's not a case of ionizing the atom, but it's putting the atom into a less stable state, right? It's not as happy, having a hole on the K shell and a space, that electron filling the space up in the M shell. And so at some point, it's going to settle back down to its ground state and fill this hole with electron from, one of these other shells, and it might take some time to settle in. But of course, what happens then is it gives off energy when that happens. And we'll see more about that. Okay. And frankly, also, if we have an ejected electron and we have a complete hole there, it's probably going to get filled unless this thing, remains in that unstable state long enough to actually bind with something else. But in most cases, an electron from space will find its, usually maybe a higher level electron, and then there's a hole up here, and basically it could be multiple processes before this thing reaches back to the ground state. But that's the idea. Okay, so we're seeing these atoms that are interacted with going out of the, because energy is deposited in them, they're going out of their happy, stable ground state and into a metastable or unstable higher energy state. Some examples of particulate radiation are alphas. And this is a little bit interesting to me because I didn't actually go and look up the origins, but we start with alphas and betas. Okay, and for some reason, alpha is actually a helium nucleus, which amounts to 2 protons and 2 neutrons, which is, as far as particles go, that's a lot of mass, right? But that's an alpha particle, and there are some radioactive isotopes that actually give off alpha particles. The beta particle is one we're going to hear about a lot, and beta particle, of course, can be charged one of 2 ways. Most commonly, we think of the electron, right? And we assign, again, positive and negative, that's arbitrary in many ways, but we assign the electron the negative. And so that's general, when we refer to it as a beta, it's a beta minus or beta negative. Or the positron, which we don't find in nature very much, turns out. And so kind of the default thing in nature is the electron. And so we're more familiar with those. Positron is the same thing as an electron, only it's charged the other way. So it's a positive charge. And so they're both betas, they have the same mass, just different charges. Okay. And because it's in the name of PET imaging, this is the key thing in PET imaging. Okay. And so we'll be seeing more of those. Protons, neutrons as the other atomic particles. And so these are nuclear particles. They exist in the nucleus, and sometimes there are radioactive isotopes that give off protons, some give off neutrons, right? And so basically, all of these things are potentially emitted from different radioactive isotopes, as we'll see. Now, the properties of these things, the alpha, of course, has very high mass because if you remember, protons and neutrons have approximately the same mass, not quite, but electrons have much less mass than protons and neutrons by orders of magnitude. And so this thing that is a cluster of 2 protons, 2 neutrons is, first of all, positively charged with basically 2 positive charges, right? And a lot of mass. And so as a result, it's extremely highly ionizing. And so, in that sense, alphas are, well, particularly dangerous, in fact. The interesting thing, because of their properties and also because of the high charge, it actually doesn't penetrate very far. So like a piece of paper is really good shielding for an alpha, okay? Turns out. So this is not going to be, because it's not going to be useful for imaging because it actually can't get through much tissue. Betas, again, whether they're positrons or electrons, have relatively low mass. They are charged. They're also, highly ionizing because they often have a lot of kinetic energy associated with them. And they don't penetrate very far either, again, because of their charge, right? Their charge will cause them to be attracted to other things as they're kind of passing through material. Similarly, proton is just higher mass, right? Charged, also highly ionizing, relatively low penetration through tissue. And then you come to the neutron, and neutrons are weird. I mean, basically, that's kind of the bottom line. Yes, it's a high mass, but it's got no charge. And so as a result, it's somewhat less ionizing and has some very weird penetration properties, which we won't really go into because they're not used for imaging. Okay, but they're bizarre. I remember having some talks with guys over at nuclear engineering at NC State because there's a neutron beam line in the reactor where they do, they work with neutron beams. And it is possible to do some weird kinds of imaging with neutron beams, but usually it's because the neutrons will stimulate emission of electromagnetic photons in certain materials. We talked about it. It seemed to not make a lot of sense for biological imaging, which was the only thing I was, is my main interest, because the things with the highest neutron cross section were heavy metals. So the only application I could think of for it would be heavy metal poisoning, like mercury poisoning and things like that. And we weren't going to get very far with that one, I think. So in all of these cases, penetration depends on energy. And the energy we're talking about is the kinetic energy, right? In other words, how fast is it going? Okay. You might remember 1/2 mv squared, which up to a point works as classical mechanics for kinetic energy. So it depends on both the mass and the velocity. We'll see when we talk about relativity that doesn't quite hold all the time. Okay, and so the uses for these things, most of the particles, especially the heavier particles, really only for radiotherapy, where you actually want to do damage. Okay, and we were going to talk about radiotherapy when we talk about radiation biology. But of course, because alphas and protons and neutrons are, they don't penetrate very far in tissue, and they are potentially damaging, then they're only really useful for actually causing damage, which is the whole idea behind radiation therapy. Alphas, alpha emitters, even though they don't penetrate very far, if you put them like right next to your target, then they can do a lot of damage. And in fact, there was a case of, well, actually, there's a case reported today, but I don't know if it's polonium, of a Russian dissident defector who was poisoned with polonium in his tea, and that was an alpha emitter. And so getting it into the digestive tract caused a lot of direct damage, apparently, and that ended up killing him. Okay, so for imaging, no, we're not using alphas, protons, or neutrons. Betas, yes. And so this pops up in a couple of different places. Also for radiation therapy, in fact, most radiation therapy, or I shouldn't say that, a lot of radiation therapy can be done with electron beams. But it's going to pop up in X-ray production, PET imaging, and so forth. So we're going to be mainly interested in the beta particles, electrons and positrons, for imaging purposes. Okay, so let's talk about electrons, because it's mostly, again, mostly electrons, but because we tend to manipulate electrons for our purposes. Positrons, happen because they're emitted by radioactive tracers, and we have a lot less control over them. Okay, so if I have an energetic electron, that means it's a moving electron, and so it has its mass energy and its kinetic energy. How do they lose energy to a medium? In one case, and this is a lot of what we've been describing, is collisional transfer. And so the electron interacts with orbital electrons in an atom. And so if the energy is high enough, you can get ionization, right? And so it kicks out an electron. If it doesn't deposit enough energy for ionization, it manifests itself just as heat. Okay. And because we have to conserve energy, right, in that interaction, the incoming energetic electron is going to lose kinetic energy. It's going to slow down. Okay. Conservation of energy. The other thing that can happen is radiative transfer, which actually kind of involves some of this also, but ultimately you balance the energy equation by the production of an X-ray. Okay, and so there are two types of those, and we will talk about. One are the characteristic X-rays, and one is Bremsstrahlung, and we'll explain each of those in a second. But the point here is really, okay, how do we balance the energy equation in order to conserve energy? And so we look at, in the interaction, what is produced, right? So ionization, technically frees an electron, therefore it transfers some energy from the incoming electron to another electron and gives it kinetic energy, right? Or heat, which eventually is dissipated in the medium. Okay. And so, those are some ways to balance the equation, but also production of X-rays can balance the energy equation as well. Okay, so this is, cartoon to kind of describe what might happen. Oh yeah, so we had alphas and betas, and here you get deltas, which I never see anyone refer to. This is kind of from an old book, but it's a good cartoon. So we won't really be talking about deltas in any way. However, the idea is the energetic electron comes in and might interact with multiple things along the way. I think this is meant to be another electron that gets kicked out until this guy deposits all of his kinetic energy and it ends up getting sucked up by an atom. eventually. In the other case here, we're actually ejecting let's say a K-shell electron from the atom and ionizing it. And so what has to happen is eventually that hole has to be filled. If it's filled by a electron from a higher orbit, then that's got to give off some energy, and it gives off that energy in the form of a characteristic X-ray. The reason it's characteristic is because for a particular atom, for a particular material, right, the energy levels of those electron shells are defined. They're very specific, and so this is a way, for example, to identify materials, right? If you bombard a material with energetic electrons and read the characteristic X radiation that comes off of it, you can, whatever, depending on the energy of this, you can determine what material that is, because it is specific to a particular material. And there may be multiple characteristic X-rays, because there's several shells, maybe in at least heavier atoms. There are several shells that could be losing energy, or it could be a combination of things, right? You could have a higher order come down to the next order, and then one from there come down to here, and that's 2 X-rays of lower energy. Okay. But in the end, right, all of the energy has to balance out. Okay. The third possibility is what's called Bremsstrahlung, which is German for breaking radiation, breaking as in slowing down. And the idea here is that this electron, as it passes and has kind of charge-charge interaction with a nucleus of an atom, essentially loses some kinetic energy, and in losing that kinetic energy, it actually has to give it off, and it gives it off in the form of a X-ray. Okay. And for some reason, it's always drawn as like taking a curved path there, which isn't necessarily the case. And in fact, this idea is kind of a cartoon way of looking at what's going on, of just trying to kind of explain what the inputs and outputs to the system are. All of this is going on at a quantum level that I don't even think I could explain without doing a lot more reading. So we see the evidence of this process, and the evidence is that electrons on a material will produce a lot of X-rays over a very wide range that are not characteristic X-rays. And this is a way of explaining what's going on, is that these electrons are losing their energy, part of their energy, and giving it off in the form of X-rays. And if, in thinking of it in this cartoon way, you can think of the electron as, okay, well, it depends on how close it gets to a nucleus as to how much energy it's going to have to lose, right? How much it's going to slow down, essentially. And so, if you have a whole population of electrons going into a material, well, it's going to vary a lot as to how much they're affected by that. And so that's a way of explaining the range of energy that you get from that process. Of course, energy, so electrons lose energy in materials. That's more or less what we're trying to establish here. And, it varies, those properties vary with material. This is a chart that's sort of plotting the energy loss as a function of electron energy. And the electron energy is going to translate directly to velocity of the electron. Okay, so how fast it's going. And this is meant to kind of describe, okay, what's the relative amount of energy loss due to collisional transfers, which were these guys, okay, just kind of bouncing around and slowly losing energy in the form of heat a little bit at a time, versus the radiation losses, which are B and C in this, basically giving off energy in the form of X-rays. And the bottom line here is that in most of, certainly in the diagnostic imaging range, which is labeled in yellow here, most of the energy loss, as we kind of go up there, is actually collisional transfers rather than radiation losses. But as you get up into high energy stuff as used for therapy, then they're much more getting closer to being on the same order. Okay. Which basically says in most, it depends on the material, obviously, in water versus lead. And people are a lot like water, by the way, we're mostly water. So, we're probably operating in this range. And so the point is that most of the radiation is losing energy as heat in a body. But there is some small percentage that is producing radiation. And notice that, well, in a body or a biological thing that's like water, it's way down here off the chart. If we're working in metals, then we get somewhat more denser materials. We get somewhat more energy loss and production of radiation, which, as we'll see, is how we produce X-rays. Okay. So the characteristic X-rays, as we said, are, go back to here, is this process where, basically we've opened up a space, and so the space has to be filled by a higher energy electron, and those are going to be very specific, right? The orbital energy levels are well defined for individual elements, and so that the X-rays given off are going to be specific to specific materials. And it is the transition into the K shell that are going to be the most important ones, the K shell being the one, what we think of as the lowest energy state. Okay. Even though there are transitions into L shell and so forth. For the most part, especially for the lighter elements, these are the energies of the characteristic X-rays are very, very low. And in fact, they're so low that if they are produced in the body from an X-ray, they would never get out, right? So we never detect those. They're well below anything that we could detect. So this all, for the most part, we need the heavier elements and getting into the metals and denser elements in order to be producing characteristic X-rays that are even in the range we could detect. So this is another slightly more detailed diagram that's showing the same thing, but talks a little bit about the energy balance here, right? The primary electron comes in with E0 as its energy, and then in this process of the characteristic radiation post-collision, so afterwards, in order to balance the energy equation, the primary electron is going to have E0 minus delta E being, okay, how much energy did I deposit here? How much energy did I lose? And so the primary electron goes off that way. It ejects a K shell electron, which is going to require energy E sub K. Okay, and so some of the energy lost by the original primary electron goes to that. Okay. And the rest of it, in order to balance the equation, is E sub K, which is the energy that's going to be required in order to come back to that shell. And again, that could be balanced, the E sub K part could be balanced by one transition or multiple transitions producing multiple X-rays, but they're all going to basically add up to E sub k. Okay, does that make sense to everybody? So basically, one thing has energy coming into the system. After the collision, the primary electron still has energy, but it has lost some. The ejected K electron has gained some of that energy, and some of that energy has gone into the K characteristic radiation, which is produced from filling the K shell. Does that make sense? Okay, all right. The other form, Bremsstrahlung, is German for, literally German for braking radiation. And, you know, as I think I kind of explained this, hopefully fairly well, the incoming electron actually slows down. So it doesn't produce, you know, it doesn't kick out another electron. That's maybe the big distinction. It actually, in slowing down and losing some of its own kinetic energy, has to balance that by giving off an X-ray. Now, the only, you know, and so whereas these are specific energies of X-rays, these could be any energy up to the energy of the incoming electron, right? I mean, he can't lose more energy than he started with. And so, you know, if that incoming electron is coming in with 100 keV energy, we could see Bremsstrahlung X-rays of anything from 0 to 100 keV. Okay, whereas these are very specific. Okay, so as an example, if we kind of look at, you know, what we see, just look at the kind of the top one here. And so along the bottom here is the energy of the X-ray in keV and the relative X-ray intensity. And this, we'll see charts like, we'll look at more charts like this later and go into more details. But the point here is that actually the, use my tablet, the Bremsstrahlung radiation is usually modeled as going like this. Okay, but because there is a medium for everything to pass through, the lower energy stuff doesn't really make it to our detector, so we often don't detect it. Okay, but basically this broad range of energy and just almost everything under this curve is considered Bremsstrahlung. Okay, but you see a couple of spikes here at very specific locations. Oops. Oh, that's weird. Never did that before, sorry. Oh, that's cool. I didn't know I could do that. Okay, there. All right, so the characteristic radiation, and this is for tungsten, has very specific spikes here, and that's it, right? Those are the characteristic peaks. And, you know, if it wasn't tungsten, if it was some other material, these would be in different places. Okay. So that's the distinction. And, you know, we'll find that when we produce X-rays, most of what we're producing is Bremsstrahlung, but there is some characteristic radiation. Okay. All right. This is like a rough approximation here. And so, you know, the efficiency of production, basically, you know, by that we mean the ratio of, you know, how much X-ray energy is produced to the incident electron energy. Okay. Let me clarify this a bit. So it depends on what material our electrons are interacting in, right? and then voltage in electron volts. And so if we were going to, sit down and work this out, this exercise, X-ray production, 100 keV electron beams on tungsten. So basically 9 times 10 to the minus 10. Tungsten is Z equals 74, and then 100 keV. And I should have worked this out before class, but didn't. So let me consult my calculator. Just a moment. Anyway, you can imagine it's going to be a very small number. Okay, let's see. Okay, so basically what we got? Right, so it's, so in this example, it's, here we go, 0, 0, 6, 6, 7. So so the point here, okay, is less than 1% of the energy produces X-rays. All the rest is heating. And we'll see that when we look at X-ray instrumentation and talk about X-ray tubes, most of the technology and a lot of the effort in X-ray tubes goes into dealing with heat, actually. It seems like a very wasteful process, and is, but this is how it's done. It's little, and it's actually, physically very hard to make it any more efficient, because that's what we're doing. We're just taking energetic electrons and bombarding something with them in order to produce X-rays. And so it's actually relatively, extremely inefficient. There you go. Okay, we'll see more about that later. Okay. Here's where we bring up Einstein, okay, and E equals mc squared. Now, the thing to think about here is that this relationship basically, actually, I can annotate this a bit. Basically describes the mass energy of a particle, or anything with mass, really, right? You can plug yourself in here and see what your mass energy is also. And the idea, of course, is that basically we're talking about the mass of the particle and speed of light. Well, that's defined here. Okay. So if you were to take a particle and convert it from mass to energy, this is how much energy you would get. Okay. However, there is one little issue that we have to deal with here, and is this thing. And this is where relativity comes in. Is that mass that we use in this equation might not be the rest mass of the particle, okay? In other words, this is the rest mass, so it's not moving, right? And this is what its velocity is. And the point here, of course, is that if it's if its velocity is 0, then m equals m0, and then everything's fine. Great. But as the velocity of the particle increases and starts to approach, let's say, the speed of light, okay, what happens? Well, this becomes greater than 0, right? Which means this term becomes less than 1, which means the relativistic mass actually increases from the rest mass. Okay, and that accounts for the kinetic energy. Okay, but this is so yeah. Okay. And so this relates to the total energy of the particle. So when I get down to here, E naught is the rest mass energy for velocity equals 0. Okay, and E is total energy. Whoops, sorry, getting a little wacky here. From the equation above. And so the difference between those is the kinetic energy of the particle. Okay. Does that make sense? I mean, if you kind of come back to this whole chain of events, right? If the particle has velocity, then the mass increases above m0, and so you're going to get a total energy that's greater than E0, okay? And that accounts for the kinetic energy of the particle. You'll notice, and hopefully this makes sense, right? As we accelerate the particle to getting closer and closer to the speed of light, the mass increases and increases and increases, meaning it's going to require more and more and more energy to accelerate that particle. And to get it to get that particle up to the speed of light, theoretically, according to this, right? Velocity becomes c, this becomes 0, the mass becomes infinite. It would require an infinite amount of energy to get it all the accelerate it all the way to the speed of light. Okay, so there's kind of a asymptotic wall out there that we're not going to be able to accelerate a particle that much. Okay. Any questions on that? This part is one of the things that's one of the harder concepts for people to pick up on. Okay, and so it's worth thinking about it a little bit. But once you start to think about it and work with the equations a little bit in our second assignment, you'll have that opportunity. It starts to make sense. Okay. Okay. So so we could say, okay, the rest energy of an electron, if this is its mass, and then we use the speed of light, which, if I remember correctly, is 3e8 meters per second. And of course, it's at rest, so we're talking about E naught for the electron. Then we just plug those in, mass c squared, and that's going to give us what, gram meters squared per second squared, which is probably joules. However, if you were to go ahead and plug this in and do the conversion to electron volts, you would find that that's 511 keV. So we'll talk more about that in a bit later. That's a kind of a magic number that we are going to see a lot. The proton, I don't remember, but you could plug it in and calculate it. Okay, so we won't do that because that's nothing but plugging into the equation, right? Okay. And so that's all we're going to say at the moment about particles, right? And again, for particles, we were really only concerning ourselves with electrons, but this applies to, you know, if you accelerate protons, neutrons as well, this equation applies. Okay. Now, so we talked about, you know, how they interact with atoms and lose their energy, which is going to be an important process in a couple of cases here. And so we'll move on to electromagnetic radiation, right? So, you know, obviously when this happens and we produce X-rays, either through characteristic X-rays or Bremsstrahlung, we have produced electromagnetic radiation. The photon, the idea of a photon is again, you know, kind of a cartoon model that we use because it's convenient. It helps us kind of conceptualize certain things. And we aren't really dealing with stuff on the quantum level, thankfully. So, you know, it's important to understand that if we can consider electromagnetic radiation in the form of photons, they're conceptually like particles. In other words, they have, you know, they travel in a direction at the speed of light or close to the speed of light. So they have a velocity and a velocity vector. And we think of them as having, you know, interactions that can cause them to essentially change their direction of travel and things. But just, you know, and we're going to talk about them in that way, but just understand that, you know, that's a bit of a cartoon that makes it easy for us to understand and probably isn't what's going on at the quantum level. Okay. I heard a physicist basically describe everything they do in physics as nothing but cartoons. Okay, that just make it easier for us to conceptualize. But it works, and you know, rather than calling it a cartoon, it's fair to call it a model that bears up under at least a lot of observation and so forth. So photons are kind of virtual particles in a sense, but they have no charge and no mass, unlike the electrons. Okay, and they are considered to be kind of energy packets. Okay, so they're little containers of energy, if you like, because for our purposes, the wavelengths of interest are much smaller than the scales of the typical interactions we are talking about. It's fair to use the photon model rather than having to deal with things as waves and deal with things like diffraction and so forth. Those kinds of interactions. Again, those things happen, but on the scales that we're interested in, those effects, you know, are not substantial. Okay, and that's because when we're dealing with the kind of X-rays and higher energies, the wavelengths are so small. Okay, that things like diffraction and stuff happen on such a small scale that it just doesn't really impact us all that much. Okay, so here's a key thing to know, because if you go back to this chart, right, we have, it labels X-rays here and gamma rays here, but in fact, that's confusing, okay, because, and sometimes gamma rays are referred to as gamma particles, even though they aren't particles, right? So gamma photons might be a better point. The point is that physically these are the same thing. They're electromagnetic radiation of a certain energy, okay? And the only distinction between them is where they come from, really, which if you're just detecting them out in the world, you don't know where they came from because they look the same. X-rays are produced by energetic electrons striking a material, as we talked about, okay? And in most cases, that's man-made, but that can be secondary effects of radioactive decay, because some radioisotopes give off electrons, and they give off energetic electrons that interact with other material, and then that interaction causes an X-ray. Whereas gamma rays are produced directly from the radioactive decay of material. But you could make you could use an X-ray source and create a 100 keV X-ray, or have a material that radioactive material that gives off 100 keV gamma ray, and they are physically the same thing. After they're produced and they're out in the environment, and let's say we detect them, we don't know which one it came from because you can't tell them apart. Okay, does that make sense to everybody? So that's why this is worth being careful with. The way they're labeling them is the ranges over which those are typically used by us. Okay, so X-rays generally are lower energy. We use lower energy X-rays to do imaging than the gamma rays we use in imaging, but there's a range of which that overlaps, because we use X-rays up to 150 keV, and some SPECT agents use 90 keV gammas, right? So they have crossed over each other. So again, this is kind of my constant warning that this is very misleading. Those are the same thing, and that whole range should be X-rays and gamma rays, really. Okay. Some of the conversions, because units are going to be important, right? It's physics after all. And so there are conversions between these different things. So basically, a photon can be described by either its energy, its frequency, or its wavelength. And these are all related to each other through these different relations. Okay. This kind of illustrates it a little bit. And so basically, frequency, energy, and wavelength are basically just alternate ways of describing a particular photon. So a 100 keV photon, for example, will be of a particular frequency and a particular wavelength. And a 200 keV photon will be of a different frequency and a different wavelength. They all have the same velocity because they all go the speed of light. So 3 × 10⁸ meters per second. But this just describes the conversions between these different things. And so basically, if you know one of these, if you know the energy of a photon, you can find out what its frequency is and what its wavelength is straight away through these conversions. And Planck's constant h pops up in a lot of these. And so a lot of it is just managing your units, which is a thing to just pay attention to the units and you'll be fine. Okay. And so as I alluded to previously, and we will talk about some more, the process of producing X-rays actually involves both of these. And we'll get into this more when we talk about X-ray systems, but the basic idea is, okay, we're going to, in the X-ray tube, we're actually going to bombard a target with energetic electrons, therefore particulate radiation, and those energetic electrons are going to produce X-rays, both characteristic and Bremsstrahlung, EM radiation, which is then going to pass through, let's say, our target. Much of it is going to pass through our target. Some of it's going to interact in the target. And the X-rays that make it through to our detector, here, again, this is old, so it says film, but those X-rays in our detector are going to deposit energy in our detector, right? That's when we get to talking about detectors, the basic idea is, okay, we've got to get the X-rays to give up their energy so we can detect them. Otherwise, they're going to pass through. Okay, so we talked about electrons interacting with matter previously. Electromagnetic radiation has basically 4 interactions with matter, but we're going to get into those next time. Scatters, 2 types of scatter, photoelectric effect, and the idea of pair production, which is much higher energy stuff. But not going to go into detail on that right now. Okay. And with the time we have left, I do want to talk about radioisotopes. And so again, kind of referred to this. Gammas are given off as unstable or metastable isotopes, go to a more stable atomic state. That's the idea. I mean, you know, we talked about electrons causing an atom to go to, you know, an unstable or metastable state, and then the concept was that, okay, pretty quickly that hole gets filled and it gives off X-ray radiation, which is what happened. The idea behind radioisotopes is the same one. It's just that if they're in, you know, metastable, basically says, okay, they can kind of stay that way for a long time, but they're still, you know, ultimately unstable. These isotopes will tend to stay in that unstable state for a long time until they make the transition to go to the more stable ground atomic state. And so the idea is kind of the same, right? And then for a given isotope, you know, again, the nuclear transitions are well defined because the energy shells are well defined. Right? And so a given isotope will emit specific energies of gamma photons. Sometimes some give off multiple energies because there might be multiple ways for it to get to its ground state. Okay, again, just to get used to some of the terminology and things, like this is stuff you've seen, right? The nucleus will have Z protons and N neutrons, and so in order to balance the charge, the orbital electrons will also be equal to Z. The atomic number is Z, right? That's how many protons we have, and that is associated with the name of the element. The mass number is going to be protons plus neutrons, and again, neutrons aren't always the same number as Z. And so a symbol for a particular element, you know, might be described this way, right? Carbon 12-6, where its mass number is 12 and it has 6 protons, therefore 6 neutrons in that case, right? Carbon 12, another way of looking at it. So in the radionuclides, right, some are natural. The only ones we use are man-made. They have unstable nuclei, and so they can basically undergo a spontaneous decay event. And in the process, they can emit all kinds of different things, both particles or EM radiation. The naturally occurring radionuclides like uranium and radon are, you know, very long-lived, and so they're, you know, kind of almost stable. They're again, you still call them metastable because eventually they will decay, but they have very long half-lives, and so are able to remain in the environment, you know, as these things for a very long time. But they do give off radiation. Because they are so long-lived, they're not really useful to us, right? So we don't use them medically. The man-made ones, which you make in a variety of ways, but in general, you're going to start with some base atom and inject energy into it to get it into the metastable state. you know, there's a bunch of examples of these. Okay, so both for therapy as well as diagnostic imaging kind of things. And, you know, again, we'll get into the properties of more of those later. But the idea, of course, you know, being in an excited state, eventually that atom wants to go to the ground state. And so stability really can have a lot, well, a good indicator of stability is number of neutrons over number of protons. And, you know, for things, for basically the smaller atoms, the lighter atoms, most of them are going to be very close to 1. And as you get to much higher Z atoms, then that the kind of the stable ratio actually increases to 1.5. In other words, they're going to have more neutrons in order to kind of stay stable. But, you know, for the light, this chart just shows the light atoms and shows that they pretty much follow close to 1 in that ratio, although not in every case, right? Okay, and so these are some weird terms that are like all almost the same. And again, just good to kind of pay attention to them. We can have an isotopic transition, in other words, isotopes. We can have isobars, an isobaric transition. We can have isomers, isomeric transition, or isotones, an isotonic transition. And each of those basically imply different types of transitions, like losing a neutron for isotopes. Isobars would basically lose a proton and gain a neutron. Again, you can think of, well, we will tend to think of it as the proton converts into a neutron and something else, as we'll see. But again, at the quantum level, that may not really be what's happening. Isomers are really just about energy being lost from the nucleus, so the nucleus being in a less stable state, and you can think of it as compacting better or reaching a happier place. Isotones might lose a proton. This is easier to see when you look at like a chart. If you kind of look at a chart of atomic number of protons versus number of neutrons, then these transitions are different directions on this chart. Okay, so for example, we're most familiar with the term isotope, and we usually refer to anything that's radioactive as an isotope. But in talking about these transitions, the stable states are like carbon-13, carbon-12, but there's carbon-9 all the way up to carbon-16. All of these are carbon because they have the same atomic number, but different numbers of neutrons in the nucleus. And again, because of, you can think of how the nucleus packs together and the forces that hold those particles together. Some of those are going to be more stable than others. And so that's the point, right? These are less stable. Carbon-12, carbon-13, more stable. Isotonic transitions are along this direction. And so we basically keep the same number of neutrons, but we change the number of protons. Okay? And so those would actually, we would actually change the name of the element in those transitions because the atomic number determines the name of the element. In isobars, we were talking about effectively converting a neutron to a proton. And so those would move diagonally along this, and basically, again, that's going to change the name. Okay. And I think I'm going to stop here, but I just want to show these. These are actual examples of these. Technetium-99m is a very common radioisotope used for SPECT imaging. Okay, and it's a 99m because M stands for metastable, and so it basically it has extra energy in the nucleus. We can kind of consider it, and so as it goes from 99m state to the 99 state, it gives off 140 keV photon. Okay, but it actually stays the same. And so this is an example of an isomeric transition. An isotopic transition is iodine 131 decaying to iodine 127. This is used mostly for therapy, but also a little bit of imaging. And so basically it remains iodine. It basically ends up losing neutrons. Okay, so isotope. An example of isobar is actually, that's not the only way iodine 131 can go in coming from its unstable state. It can also decay to xenon 131, where 131 is the Z plus N number, okay? And so this is the the effective conversion from a neutron to a proton here. Okay, so the atomic weight kind of remains the same or roughly the same, but because it has a different number of protons, we call it a different element. And so this actually is an example of, this is an isotope that if you have a bulk amount of it, some of it will go this way and give off the appropriate energy for that, but some of it will go this way and give off the appropriate energy for that. So this is sometimes considered a messy, slightly messy isotope because it doesn't, it gives off more than one energy of gammas. I'm going to stop there. There's still a little bit more to talk about with some of the specific types of nuclear transitions, but we'll get to that next time. So, any last questions?
On the material that we talked about today, or?
Yeah. Well, on anything.
Oh, okay. I was wondering about question 5 on the homework.
Okay.
So
let me go find it.
I mean, I can tell it to you. It's how does a linear filter affect the NEQ of an image? Show this mathematically. And I guess I know intuitively what a filter is going to do to the NEQ just because it's an evaluation of noise in signal.
Right.
But when showing mathematically, do we use the kind of big formula that was on the PowerPoints and like derive the NEQ from that?
Well, okay, so let me frame this a little bit. Where was it? It was here. Okay, so first of all, I just want to be clear that we're kind of talking about this process. So let's say we have a raw image G, and we're producing a processed image, and the question kind of refers to, okay, how does this affect, we have a certain NEQ at this point. How does this change the NEQ? Okay, now the relationship on that is going to come from the idea of, okay, what happens to a power spectrum, because let's go, roll down to NEQ. NEQ is a basically frequency by frequency ratio of power spectra, signal power spectra and noise power spectra. Okay. So how is the power spectrum, how does the filter affect the power spectrum? Well, I guess I had a slide specifically on this here, right? Any power spectrum is affected by a filter in this way. Basically, you're just going to multiply the power spectrum by the magnitude squared. of the filter's frequency response.
Oh, that's not
It's
too
as
bad.
simple as that. It's deceptively simple.
I guess I saw the prove it mathematically, and I kind of freaked out. How to do that.
Yeah, it's simple, but what's more important is, what does it mean in a practical sense? That's the part I think is more important, is kind of understanding, okay, what does that tell me about this? Okay, did that help?
Awesome. That helps a lot. Thank you.
Okay. Any other questions?
I'm not sure if I'm allowed to ask a question in this way, but I was wondering if I could run an approach to solving one of these problems by you, specifically number 3.
You're allowed to ask a question any way you want.
Okay, so when a system is composed of a cascade, you have to convolve the two systems, correct? So
you convolve them in the spatial domain.
Oh, I thought it was in the Fourier domain.
Now, in the Fourier domain, you would just multiply them.
Yes, exactly. So so the point being that you could take the Fourier transform of both the systems, multiply them, and then take the inverse Fourier transform.
That would be much better than trying to convolve them.
Beautiful. Okay, just making sure I was in the right direction. Yes.
Yes, I'm not a fan of convolution, of actually sitting down and doing convolution intervals. So when I ask questions related to that, I mean, you can get the right answer that way. It's just the harder way to do it.
Yeah. Okay, cool. Thank you.
Any others? Going once. Going twice. 3 times. Then I will see you all next Tuesday. Be good to get your homeworks in sometime when you can. Preferably today, but tomorrow if you have to. And I'll see you on Tuesday.
Dr. Lalish?
Yes.
Assignment 2 wouldn't be assigned until next week, right? It wouldn't be like due next week, would it?
No. The kind of the day that it's kind of shown on the schedule is the day we at least finish most of the material for the assignment. So it wouldn't be until a week after that. So I'm thinking, yeah, assignment 2, probably roughly a week from the 25th. So that's going to take us into the first week of September. Does that answer the question?
Yes.
Yeah. So it won't be till next Tuesday that we really, I think, finish the material you need for that one. And we might not finish all of it, but we'll finish most of it. And so you would have at least a week after that.
Okay, thank you.
Okay. Okay, last chance. All right. Okay, see you next Tuesday then. Have a nice weekend.